Hello guys, and welcome to my channel. In this video we will break down the complete C build process, from writing source files to compiling, linking, configuring compiler settings, fixing errors, and debugging C programs. Before we write serious C code, especially for embedded systems, we need to understand the compiling environment. A C program is not converted into a runnable application in one simple step. It passes through a complete toolchain: the code editor, preprocessor, compiler, assembler, linker, and finally the executable output. The source files contain our program logic. Header files describe interfaces. Libraries provide reusable functions, and compiler settings control how strict, optimized, or debuggable the build will be. In embedded C, this environment is even more important because the output may not be a normal desktop executable. It may become an ELF file, hex file, bin file, or firmware image that is flashed into a microcontroller. The compiler must also know the target architecture, such as ARM Cortex-M, AVR, ESP32, or RISC-V. My professional advice is this: never treat compiling as just pressing a build button. Understand the toolchain, because most real embedded bugs come from wrong settings, missing paths, linker issues, or incorrect build configuration. In C projects, source files and header files have different responsibilities. A source file, usually with the .c extension, contains the actual implementation, function bodies, logic, calculations, drivers, and application code. A header file with the .h extension normally contains declarations, function prototypes, type definitions, macros, constants, structures, and shared interfaces. The include directive tells the preprocessor to bring header information into the current file before compilation. Angle brackets, like include stdio.h, are usually used for system or toolchain headers. Double quotes, like include mutils.h, are commonly used for your own project headers. A very important embedded C rule is this: do not place normal function definitions in header files unless you really know why. If you define functions in headers and include them in multiple C files, you may create multiple definition linker errors. Good header organization makes the project modular, reusable, and much easier to maintain. After understanding source files, header files, and include directives, the next important concept is libraries. In C programming, libraries provide reusable functionality, so we do not need to rewrite common operations from zero every time. Standard libraries such as stdio.h, stdlib.h, string.h, math.h, and time.h provide functions for input and output, memory utilities, string processing, mathematical operations, and time-related tasks. But technically, a header file and a library are not the same thing. The header file usually tells the compiler what functions exist, what parameters they accept, and what types they use. The actual compiled implementation may come from a source file, an object file, or a precompiled library. This is why a program can compile successfully but still fail during linking if the real library implementation is missing. In embedded C, libraries must be used carefully. Some functions, especially print, floating point math, dynamic memory allocation, or large string utilities, can increase flash usage, RAM usage, and execution time. My professional advice is to always check the cost of the library on the target microcontroller. Reuse tested code, but never blindly include heavy libraries in a memory-limited embedded system. In standard C programs, the main function is the main entry point of the application. It is where program execution begins from the programmer's point of view. The common form is int main void, or int main with arg and argv when command line arguments are used. Returning 0 usually means the program finished successfully, but in embedded C, there is an important technical detail. The microcontroller does not usually jump directly to main after reset. First, startup code runs. This startup code sets the stack pointer, initializes the data section, clears the BSS section, configures the runtime environment, and then calls main. So, for embedded systems, main is the start of the application logic, but not the first instruction executed by the chip. Inside main, we usually initialize clocks, GPIO, peripherals, drivers, communication interfaces, RTOS tasks, and then enter an infinite loop or start the scheduler. My advice is to keep main clean. Use it as the system level organizer, not as the place where all logic is dumped. Compilation happens in several stages. First, preprocessing expands, includes, and macros. Then the compiler checks the C syntax and converts the preprocessed code into assembly, or an intermediate representation. After that, the assembler converts assembly instructions into machine code and stores them in an object file, usually with the .o extension. An object file is not the final program. It contains compiled machine code, symbols, and relocation information, but it may still refer to functions or variables defined somewhere else. That is why the linker is needed later. For embedded development, object files are very useful because each C file is compiled separately. This allows large projects to rebuild only the files that changed, instead of recompiling everything. My comment here is, when you see a compile error, it usually means the compiler could not understand one source file. When you see an object file generated successfully, it means that file is syntactically compiled, but the full program may still fail during linking. Linking is the stage where separate object files and libraries are combined into the final program. The linker resolves symbols, connects function calls to their real implementations, combines code and data sections, and produces the final executable output. In embedded C, linking is extremely important because the linker also decides where code and variables will be placed in memory. This is controlled by the linker script. The linker script describes flash, RAM, stack, heap, interrupt vector table, text section, data section, and BSS section. If the linker script is wrong, the firmware may compile successfully but fail at runtime. Common linker errors include undefined reference, missing library flags, wrong library order, and duplicate symbol definitions. An undefined reference usually means something was declared, but no actual implementation was linked. My professional advice is always inspect linker errors carefully. They are not random. They usually point to missing source files, wrong build configuration, or functions declared in headers, but not implemented correctly. Compiler flags control how the compiler behaves. They are not just optional settings. They directly affect code quality, performance, debugging, and portability. Flags like -val and -vextra enable important warnings. In professional embedded development, warnings should be treated seriously, because a warning can become a real hardware bug later. The flag -std equals C11 selects the C language standard. Optimization flags such as -o0 and -o2 control how aggressively the compiler improves the code. -o0 is useful during debugging because the generated code stays closer to the original source. -o2 is common for release builds because it improves speed and often reduces code size. The -g flag adds debug information so tools like GDB can map machine code back to source lines. Include paths use -i. Library paths use -l. Libraries are linked with -l. My embedded comment is, always separate debug and release configurations. Debug should help you understand the code. Release should be tested carefully, because optimization can expose timing problems or undefined behavior. A good C project needs a clean build environment. The project should be organized into clear folders, such as source, include, lib, and build. Source files contain implementation. Include folders contain public headers. Lib folders contain external or precompiled libraries, and build folders contain generated output files. The main tools in the environment are the code editor, or IDE, compiler, terminal, build system, and debugger. In embedded systems, the compiler is often a cross-compiler, meaning it runs on your computer but generates code for a different processor. For example, ARM-, NAND-, EABI-, GCC runs on Windows or Linux, but generates firmware for ARM, Cortex-M microcontrollers. Build systems like Make or CMake automate compilation and linking. They make the process repeatable, which is very important in professional work. My advice is simple. Do not rely only on manual IDE settings. Keep your build configuration documented and reproducible. A project that only builds on one person's laptop is not a professional embedded project. After compilation and linking, the program must be executed and tested. On a desktop system, running may be as simple as executing the generated app. In embedded systems, running usually means flashing the firmware into the microcontroller and starting it on real hardware or in a simulator. Debugging helps us find runtime problems, not just compile time problems. A program may compile perfectly and still crash, freeze, reset, or behave incorrectly. Debug tools allow us to set breakpoints, inspect variables, step through code line by line, and analyze the call stack. In embedded systems, Debugging often uses GDB together with tools like OpenOCD, JLink, ST-Link, or ESPprog. The example with division by zero is a good reminder. The compiler may not always stop dangerous logic. On a microcontroller, runtime faults may appear as hard faults, watchdog resets, or unexpected behavior. My professional advice is debug with both software tools and hardware observation. Use breakpoints, logs, LEDs, oscilloscopes, and logic analyzers when needed. C projects often fail because of simple but important mistakes. Missing include files happen when the compiler cannot find the required header. Undefined reference errors happen when a function is declared, but its implementation is not linked. Multiple definition errors usually happen when variables or functions are defined in headers or duplicated across source files. Syntax errors come from invalid C code, and ignored warnings can hide real bugs. Best practices reduce these problems. Use header guards in every header file. Enable warnings early with flags like -vol and -vextra. Keep source files and headers organized. Use meaningful compiler flags. Separate debug and release builds. Build and test small changes frequently, instead of writing a large amount of code before testing. My professional comment is this: embedded C is not only about writing code that compiles. It is about writing code that is predictable, portable, testable, and safe on real hardware. A clean build system, strict warnings, and good file organization can save hours of debugging later. Thanks for watching this video, guys. Please share, like, and comment below. Also subscribe to my YouTube channel for more videos.